Hi, everyone. Today we're going to discuss phase retrieval techniques for optical pulse characterization. In particular, we're going to focus this discussion more intently on FROG, which is frequency resolved optical gating. It's only one type of technique that is capable of retrieving both the amplitude and phase of an optical pulse envelope. But there are other techniques, and they're mentioned here with a few links to key papers, and I would encourage you to sort of broaden your reading after today's discussion and going through this lesson online. Frequency resolved optical gating or FROG is probably the most common technique because it is quite simple to implement. That doesn't necessarily make it the best technique in every circumstance. There's pros and cons, of course. So definitely you should read around, and hopefully this spurs your interest more than anything in these techniques in general. So as usual, we have we have amended our running list of packages and functions and custom code that we have for doing our calculations, and that includes the calculations in this lesson. I've listed out here for convenience the newly added functions that we're going to be using for our FROG analysis. These won't make so much sense now, but I'm just listing them here for convenience so that you can go back later when you see these in the code later on in the lesson, and you can refer back here to see what the new parts are. Because as you can tell, this is quite a long list, and I've chosen to leave everything in here as we go, with the hope that by the end of all of this, you have one very large list of functions and packages that you can immediately start using in Python, maybe save it as a .py file or .py file that you could import and really do almost everything you want to do in Ultrafast with this starter code and starter functions that we've built up. Okay, so definitely take a look through the new functions. They're all at the bottom, listed out as these FROG analysis functions. So let's start with our discussion a little bit more broadly. So getting away from FROG specifically and talking more broadly about why phase retrieval is needed at all. This goes back to our very first discussions on ultrafast optical pulses and how we denote them mathematically as having an envelope that is complex, and it has both amplitude and phase terms. And we've learned through all of our discussions to date that the amplitude and phase are both critical to describing an optical pulse. You know, in time, the time average energy is described by the amplitude, the magnitude of this amplitude function, but the phase tells you about the dispersion that has been encountered by that pulse. Also, it tells you whether that pulse is truly transform limited or not. If I measure a pulse in time, I don't really know if I have potential to further compress that pulse. I could look at its spectrum and look at its time domain envelope and kind of discern that it is or isn't transform limited, but I don't know what I need to do to that pulse to get it to be shorter unless I understand the phase and the shape and the properties of that phase. So phase retrieval is extremely important in ultrafast optics to both achieve very short pulse durations and properly manage these pulses in our systems. So that's the motivation for why phase retrieval is needed from a conceptual point of view, and then why do we need to perform some type of phase retrieval technique like FROG, which we'll discuss more about how it works, but I mean, suffice it to say, it's a lot more complicated than just sticking a meter inside of an energy meter inside of my beam and detecting how it changes in time. So why can't I just do that? And I think that's kind of where we'll start, and that's kind of important to motivating why we need to work so hard to measure these amplitudes and phases of optical pulses. So let's imagine I have some optical pulse. It has this envelope here. in time, and we have some waveform. This is not necessarily meant to be to scale, but just to remind you, right, you have some amplitude function that gives you this pulse envelope, and then you have the waveform underneath. And let's say that that's traveling here to a detector, right? And so this is going to be some kind of energy detector. And so this would be some electric field as a function of time, right? And then this is going to spit out a current here, I, as a function of time. So the difficulty here is that these pulses that we're interested in, at least that we've been discussing heavily in this course, they have been on the order of tens to hundreds of femtoseconds, right? You can have, of course, fast pulses that are on the picosecond to nanosecond range, but really, truly, ultra fast pulses, right, that we're interested in mostly are on this tens to hundreds of femtoseconds range. And the problem here is that typically most detectors we have RC time constants, right? I'm just saying RC here is just effective. RC is an example. Of course, there's probably other effects, inductive effects, and everything else that play into the net time constant. So I guess really it's this net time constant of our detector, right? It's rise time. These time constants, you know, the best you can do is going to be on the order of tens to hundreds of picoseconds. And that's really, really working hard. I mean, these would be like the absolute fastest detectors that you can engineer by. You have to be very careful how you terminate them and impedance matching and all of this. There's a lot of nuance to it, but if you really, really try, you might be able to get this to tens to hundreds of picoseconds. But you see the disparity here between that and the pulse of tens to hundreds of femtoseconds. So if I shoot my pulse into this detector, I'm going to get a current pulse out that's on the order of this time constant, not my optical pulse. So there's this limitation. I can't really see inside of it. So that puts this kind of upper limit for direct detection of the envelope. There's another thing that's happening here, which is that even, let's say, even if I had the ability to detect this envelope at tens to hundreds of femtoseconds, if I measure its time average energy, right, that's the time average energy over one cycle here of that waveform. And even then, I don't have access to the optical waveform, right? And there's never going to be a detector that would be able to measure just directly in real time this field, at least not that we have to date, right? What you could do is you could think, well, this could give me my energy. Maybe I could stick this in an interferometer and do interference, right? So I don't need to measure time directly, but I could interfere two pulses. And if I look at that interference coming out of an interferometer, I might be able to then use that interference signal to see this time duration of the pulses. So let's say I have a pulse in here. It gets split into two smaller pulses, and these are just replicas of one another if we have a really true 50-50 beam splitter. And then I interfere the two here. Let's say you got these two pulses with some delay, tau, right? So now I have some delay here, I'm interfering them, and I'm going to stick my energy meter, and let's say that I have them set up to interfere, and then I have my current out as a function of time, right? So this is great. I can see when these two pulses overlap, right? If I see interference, I know they're somewhat overlapped in time. But it turns out that even this interference signal, so long as this detector is proportional to the energy, so this detector, so I of t is proportional to the energy W, so the energy, right? So if the current is proportional to the energy and you do this interference, it turns out that you can tell when the two fields from each pulse are overlapped, but when you record that interference signal, right, just because of how the physics work out, that it's a square dependence on the field, all phase information ends up being lost. And it may not be completely obvious and intuitive, but you can take my word for it. I think it's beyond the scope of this discussion today, but we can just say all phase info is lost, right? And that's when, in particular, when this current is proportional to energy, okay? So then that leaves us in a situation where what could we do? We can't stick an energy detector here. We can't use interference to get that phase information out. We can't measure the envelope in most circumstances unless we have something that's a very long pulse in the order of tens of hundreds of picoseconds or longer. So what do we do? And that brings us to the solution we're going to be talking about today, which is phase retrieval with frequency resolved optical gating. Again, there are other techniques out there, but we're going to focus on frog here. And so how does this work? It works by going back to that interferometer and making a couple of tweaks. So let's go back to our interferometer here. And let's keep all of this part. Let's see if I can do this. Paste it down here. And we still have our interferometer, right? We have our two pulses here and here. And then what we can do is, let's make an adjustment here. I'll make our edits in red. Okay, so what we can do is we can say, well, I'm not going to go straight to my energy meter. I'm going to stick a nonlinear medium here. In particular, I'm going to stick a chi2, but it doesn't necessarily have to be chi2. But I'm going to have a nonlinear medium. Now, these two pulses are going to interact in that nonlinear medium, and I'm going to have some kind of filtering process. This will be a filter, so that this only measures 2 omega pass, right? This only allows 2 omega terms to pass. So you interact these two pulses in this chi2. That makes an upconverted component at omega 1 plus omega 2. Here this is central energy of central wavelength omega. So this pulse has omega, this pulse has omega, this pulse has omega. So when they interact here, we get an output. So if we track through there, we get some output at 2 omega, right? And we're going to filter that out. That's what this filter is going to do. Now I'm going to send that 2 omega part to some detector, but instead of detecting just the intensity, I'm going to actually send this through a grating and measure its spectrum, right? So this is a spectrometer. So these are the two key changes I'm going to make to see if I can get more information out of this pulse, pulse measurement, and capture both the amplitude and the phase of that pulse's envelope. And so what I'm going to do is I'm going to have this nonlinear mixing. I'm going to make 2 omega, mix the two together, and I'm not just going to look at the energy. I'm going to look at the energy as a function of frequency. So I'm going to take its spectrum here, right? And so that gives me some intensity as a function of omega. Okay. So if I combine nonlinear mixing with the spectrum, then I actually can get phase information from my pulse. So let's go back to the math for a little bit and discuss that really quickly. So if we look here, this can be described, this nonlinear mixing part can be described as this cross correlation here. Now this is a complex cross correlation. I'm using this tilde to represent frequency domain here because later we'll talk about this cross correlation in time as well. This is a cross correlation. This is the amplitude in frequency. That's what we'll call this S as a function of omega and delay. So we have this delay parameter we can shift in when we change the delay between these two pulses. We could do that by lengthening one of these arms just a little bit. I didn't show it here. But you get the picture that if I change the delay between the two, then I will shift one of the pulses with respect to the other. Now, there is one difference here, is that I'm making this a little bit more general. So here we have this mixing term between two arbitrary pulses. These don't have to be the same pulse. They can be, that's fine. But this is just to keep everything even more general. So in this case, we'll still talk about it pictorially as just splitting apart the same pulse. But just note this, these two can be arbitrary. We have two different pulses that are mixing in that chi2 medium in that chi2 medium. That's exactly what's being shown here because we have the pulse here P, the pulse here G, they're being multiplied together. So this is a chi2 response. In this case, it's not interferometric, it's just the interaction of their two envelopes. So it's more like an intensity cross correlation between these two. All right. So then when we measure the spectrum, remember we measure the intensity spectrum. So that is this amplitude squared of this S term here that we described here. So this is this nonlinear action. So basically this S of omega t, this is what describes the pulse that comes out of that chi2. So I'm going to get a screenshot of this. All right. Screenshot. Let's carry that over to our notebook here. And then copy. There we go. So this is the mathematical representation of this 2 omega pulse here. I just wanted to keep the context clear here. In this case, these would be the same pulse, P of P maybe, but in general, it can be two completely different pulses. All right, so the next question is, okay, now I've done this. I still haven't proven to you why this carries amplitude and phase information. Now, this is a little bit more complex to just demonstrate in general why this would always carry amplitude and phase information. The reality is that it does, but we can come up with a toy system. It doesn't necessarily have to be the case, but it's a toy system that just sort of demonstrates why this tracks the amplitude and phase of the pulse. And that's by doing a couple of things. First, we'll call this function here G. We're going to call that the gate from here on out, and that will just stay true. And here we're going to assume that this gate pulse, for the purposes of this demonstration here, we're going to assume that that gate pulse is transform limited, first of all, and secondly, much, much shorter than the duration of P, which we'll call our pulse that we want to measure, right? So we have a gate that is transform limited and much shorter than P. So let's take a system. Let's give ourselves a new sheet of paper here. So let's take a system where we have a G of T that's transform limited and much shorter than P. So let's draw these two pulses here. Remember, it's really their envelopes that we're after, the complex envelopes. So this would be some P of T, which is long. And then we have some G of T here. And this would be some G of T, which is short. So G of T is short and it's transform limited. What does that mean? That means it has no phase, right? So if you look as a function of time, G of T just is a pure amplitude gate. There is no phase on G of T. Now P of T is another story. We're going to let that be arbitrary. The only condition is we're going to say that P of T, its envelope, has to be longer than G of T. But we can describe that more completely as we have in prior lessons. So P naught of T would be its amplitude function. And then we have some e to the j phi of t, which is its envelope function. Now, in general, let's say now that we can let P of T move back and forth with tau, right? So how do we get that tau in there? Well, then we say that this P of t is actually P of t minus tau, right? We can move it to the right and the left in time relative to G of t, P naught of t minus tau, e to the j phi of t minus tau. Now, let's think about what this means, that G of t is much shorter than P of t. Well, what it means is that over this duration of G of t, right, if we look here over this duration, notice that the amplitude function, this P naught of t, is not changing that much, right? It's relatively fixed, okay? Second of all, we can assume that this phase function over that duration is not changing that rapidly. So we'll assume that we can represent it with a first order Taylor expansion. So based on the assumption that G of t is short and transform limited, we can approximate this P of t function as P naught of minus tau, right? Because G of t sits at t equals 0. I should emphasize that. So this is t equals 0, right there at the center. So that means we can stick t equals 0 in here and just have the envelope be a fixed constant because it's changing quite slowly. And then we'll let phi of t be a first order Taylor expansion. So what does that mean? So that means it's going to be d phi dt, right? Evaluated at t equals minus tau times t. And then plus j phi naught. And that's just going to be some constant offset phase. And that's going to be minus tau, right? So that's going to be whatever constant offset we need at negative tau. It might change as we move this delay tau, right? So we'll let that change. All right. So what does that mean? So over this duration, G of t, we have some envelope function here, which is just a constant that is P naught of minus tau, fine. But e to the j, this d phi dt at t equals minus tau, that's some going to be some constant number here that is this first derivative of phi with t at t equals minus tau times t. But that's like a frequency, right? So this is almost like the instantaneous frequency at t equals minus tau, right? So this is like some instantaneous frequency at t equals minus tau inside of p, right? So as I slide this p function along, basically what I'm saying is that the frequency of p is shifting slightly due to the derivative of that phase, right? Well, what does that mean? That means when I mix this g of t with this p of t minus tau, I'm going to slightly shift the frequency of that some frequency term, right? It's not going to be pure second harmonic generation, or it's going to be second harmonic generation, but shifted slightly in frequency due to that d phi dt term. Okay. So what does that mean? That means, for instance, if we have phi of t, let's say that phi of t is equal to alpha times t squared, right? So that means that d phi dt is going to be 2 alpha t. And then if we evaluate that at negative tau, that means that d phi dt evaluated at t equals minus tau, that instantaneous frequency is going to be minus 2 alpha tau, right? So that means that as a function of tau, it's going to be a negative slope, right? And that it's going to go down. So if we plot it out, this the sum frequency term, this is the sum frequency, and then this is tau, you would see a negative slope to that sum frequency if you were to plot these two out. If P of t were to be transform limited, which means that phi of t is equal to 0, of course, it would just be some flat band, right? And of course, if you would have a negative alpha here, it would have a positive slope, right? Now, what if phi of t has a cubic term, right? So now what if phi of t is equal to, let's call it beta t cubed, right? So d phi dt t equals minus tau. That's going to be equal to 3 beta tau squared. Now, it doesn't matter that tau is plus or minus because of the square. So you're going to have like a quadratic term. So now you look at the sum frequency. Now we're looking at the central frequency, right? It's going to have a bandwidth to it, but you look at the sum frequency, it's going to do this as a function of tau, right? So if we look at this spectrum, or spectrogram, I should say, so this frequency space as a function of tau, you kind of see how there's a direct mapping of this phase from P imparted on that central wavelength of that sum frequency term. Okay. Now, this is a very specific subclass of these frog conditions, right? Because I'm assuming G is short and it's transform limited. I want to emphasize again, it does not have to be the case. We'll show that in the next step. But this is just to show how that phase gets imparted on these spectrograms. And so what we can do is we can do some calculations, and maybe I didn't emphasize earlier that this is typically called a spectrogram, which is where you take spectra as a function of some delay parameter, for instance. So if we plot this magnitude squared of S, this I of omega t, so if we plot that as a function of delay, what we'll see is that when we're well, I've got 3 scenarios here. And one, which is in all cases, G of t is 10 femtoseconds long, and it's transform limited. And P of t is 30 femtoseconds long. And then now P of t is going to change in terms of its phase part, right? So the envelope is always 30 femtoseconds full width half max, but I'm going to put different phase profiles in time, right, to demonstrate what we just discussed. So now let's take this first scenario, case 1, where P of t is transform limited. Okay. Plot out the spectrogram. It's exactly what you'd anticipate. You have a central frequency here. Now, central frequency 0, this is more like a frequency offset. So central frequency 0 here means just that's the sum frequency between the two, right? And then this is the difference between the sum frequency of the central frequencies of both pulses. So this 0, don't be confused by that. That's just because of it. We're going back into this envelope notation for frequency. But you see it's perfectly flat, okay? So I would say, well, P of t has no phase, it's flat, it's transform limited, right? Now let's go to the case where we have a quadratic phase. So it's important to note you can click into the code here. And if we look at the code that made this plot, what you'll notice is I take my P here and I basically, okay, sorry. So I take my pulse here and I add a little bit of quadratic phase, okay? And in this case, my coefficient is negative. So the alpha term that we showed here, I put in a negative alpha. So you'd actually expect to see a positive slope for this case. And that's exactly what you see. So if you look at that sum frequency term, its central frequency goes up linearly, right? That's really important. It goes up linearly when I put on a quadratic phase, right? Because we're basically probing the derivative of that phase. Now I go in and I do the same thing, but I put in the exact same function, but I just change this coefficient to positive, right? And now I see a linear slope again, but downward. So I can see the sign of the phase as well. Finally, this final scenario is a little bit more complex. What I did is I added in a quadratic phase here, and then also a cubic phase here, right? So this is TP is just the time for the pulse. So now we have some function of TP cubed. So what would that be? Well, what would we expect? We've got a quadratic phase, so we've got some linear function, right? Its coefficient is positive, so we'd have some negative slope downward. You have a cubic phase, which means that you have this parabola like this. This beta term is positive, so we'd expect to see an upward swinging parabola, right? If this beta was negative, we'd see a downward swinging parabola. And that's exactly what you see, negative slope, and it swings up because we've got that parabolic term from the cubic phase as well. So really neat. You can just look directly in. If you can ensure that this scenario is true, G of t is short and transform limited, you can basically just look at your frog analysis and look at the shape of the output of the spectrogram and instantly ascertain what the phase is. Okay. So there's a lot of information in there, and even visually you can see it. And I think this is something to emphasize, that if you do a lot of frog analysis and you plot a lot of these spectrograms in a lot of different situations, you start to get a feel for when pulses are transform limited and when they have positive chirp, negative chirp, all of these things, simply from looking at these spectrograms. So there's a lot of information that can be gleaned just by looking at these spectrograms visually. Okay, so hopefully to this point, we've discussed how frog analysis provides both amplitude and phase information about a pulse. Okay, so how it's encoded. We've looked at a very specific subclass of frog with sort of assumed conditions, right? But in general, again, those don't have to be true. So what we're going to talk about now is how do we approach these frog spectrograms from the context of doing a general phase retrieval. Okay, so let's just find a way to mathematically analyze these spectrograms so that we can use a computer to computationally pull out this phase, where I don't even care what the conditions are on P and G. Can I just arbitrarily retrieve them, right? And so that's what we're going to discuss in this section here. So basically, the approach that we're taking is a little bit different than the standard approach that you'll find. The standard approach is this principal component generalized projection algorithm. We'll talk about what all these terms mean. For instance, projection algorithm, all that will make sense as we go through. But I just want to note that this paper Kane et al. Here, that you should definitely check out this paper. It discusses this principal components technique, which is super elegant, but a little bit less sort of nice from a pedagogical standpoint, going over here for like learning how this works. So for learning how this works, I'm just going to introduce a simple least squares approach, which is a little bit more straightforward in understanding how this minimization process works for extracting the phase from a spectrogram. I also think it's interesting because this least squares approach is super general. You can apply this to all kinds of problems. So if you really understand how it's working in the context here, I guarantee you'll find other problems in your scientific career where you might want to use an approach similar to this least squares approach that we're going to introduce. So I think it's also just super functional and useful sort of in your research. All right, so the first things first is that what we need to do is we need to start breaking this down into terms that are more reasonable for a computer. And then secondly, we're going to introduce the idea of analyzing these spectrograms not in the frequency domain, but in the time domain. And the reason that's pretty easy for us is because they're simply separated just by a Fourier transform. Right? So computationally, it's very easy to take a Fourier transform, so I can convert between this spectral form to this time form very, very simply in my computer. And the reason I like to do that is because it gets rid of that integral. So if we just briefly go back and look at the definition of the spectrogram, right? It's this integral, which is essentially, if you note, this is just a Fourier transform, right? And it's nice to not have to have that integral inside of our analysis, right? So when we do our minimization on the spectrogram, we actually want to perform it on this time domain form because it gets rid of that integral for us. It's simply P of t minus tau times G of t, right? So it's much easier to analytically analyze this as opposed to that integral above. And in the computer, it's just a Fourier transform away. So we can simply just move back and forth fluidly. But then analytically, when I'm determining my minimization approach, I'm going to work on this time domain form. So that's the first thing we're going to do. And that's true of all of these approaches, by the way. So that's a general step. The second thing we're going to do is we're going to break it down into discrete parts. So this is a straightforward discretization of this S of t and tau. Interestingly, a lot of times analytically, we like to do t minus tau to shift something to the right. But numerically, it's actually easier to talk about shifting the other function inside of these indices. So here I'm using the square bracket to mean the nth sample in time and nth sample in delay, tau. So n is kind of the sample number in time, m is the sample number in delay. And so I can write this as P of n plus G of n plus m. If you notice, it's the same thing. I've shifted this minus delay here to a plus delay on this G term. And the reason that's a little bit easier to deal with is because normally we start with sample 0 and go up to some maximum sample. We can't sample forever, right? In our computer, we can only store so many data points. So we have a limit to how many samples that are even possible. Okay, so that's basically our first two things that we need to do. We're going to work with the time domain form of S, and we're going to discretize everything, okay? In samples and time, in samples and delay. All right. So now we're going to be, from here on out, talking about pulses in sample N and gates in sample G, okay? And remember, these are arbitrary functions. We did put no conditions on them. All right. So what I've laid out here is in steps 1, 2, 3, 4, 5. These are going to be 5 steps that will be taken to determine P and G from S. Okay. Now remember, how do we know S? Okay, so we'll talk about that here in a second. So the procedure for determining P and G is going to go as follows. I'm going to start with an estimate. So this is an initial guess, I should say, maybe not even estimate, just I guess a current estimate. You could take the transform limited pulse from each of their spectra, right? So you can either go from an estimate or just a random initial guess for P and G. Okay. If I have that initial guess, I can actually calculate spectrogram S. Okay. Now, if I perform a Fourier transform on that spectrogram, I can convert it from time space to frequency space. Okay. Now, remember, our measurement is in this frequency space. So we're assuming we have a measured spectrogram available to us, right? But remember, that measured spectrogram, right, is like this. And what is that going to be? That's going to be this I of omega tau, which is the amplitude squared of S. Okay. So that's something just to note. Okay. So we have that available to us. So what we're going to do is we're going to use P and G to calculate S, Fourier transform to get it to frequency space. Step number 3 is we're going to take the measured spectrogram, this intensity spectrogram, we're going to extract the amplitude from that and project it onto S, such that we get this new spectrum S prime. What is it defined as? S prime is the square root of our intensity spectrogram that we measured times the calculated S divided by its own amplitude. So what is that doing? It's basically projecting the phase from our guess onto the intensity amplitudes from our measured spectrogram. Now we can take that back to time with an inverse Fourier transform, and we're going to get this new S prime. And then we're going to define a cost function, right, which is going to calculate how much squared error there is between our S and our S prime, right? But what is that? Well, S is just the current pulse and gate minus, and then S prime. Remember, this S prime has our intensity spectrogram encoded into it, right? So when this error is 0, it means that our current P and G are accurate in their description of S. It's self-consistent, right? So you want M to be as close to 0 as possible, okay? So now why have we done this? 1, 2, 3, 4, 5. This seems like a lot of trouble, right? Well, this is really nice because now I have some analytic function M, which defines an error based on each sample in P, each sample in G, and our projected spectrogram S prime. Okay, so now it's only a matter of saying, well, what value of P of N and what value of G of N should I use to minimize this error? And that's what we're going to talk about next. So now we basically have defined our error M. And as we were just saying, we need to do some sort of minimization, right, of this error to determine what the next values of P and G are going to be. So the way you do this is basically similar to what you would do to minimizing any function, right? So if I gave you a complex function of a single variable, or just any function of a single variable, I should say, then if I asked you to find where it has a minimum or a maximum, I would say, well, just take the derivative and set it equal to 0, right? That's going to be where you have all your minimum and maximum, right? And if we assume that M has one single minimum, now that's an assumption, it may not, but we assume it has one single minimum, which we hope it should. If there's just one single unique solution to the pulsing gate from our measured spectrogram, then what we can do is we can say, well, let's imagine that each sample P of N and each sample G of N, that each one of those are separate single variables. And I'm just going to set my derivative of each of those to 0, derivative of M as a function of each of those individually to 0, right? And we can do this iteratively where we say, well, let's just first start with P of 0, take the derivative of M with respect to P0, set that to 0, solve it, go on to P1, P2, P3. Once you finish doing that, do that for all the G's, and then start the process over, right? Now you have a next guess for, an updated value for all of the P's, all of the G's, and then you fit that back into your routine, do this projection step, come back, do it again, right? I would encourage you to sit and sort of slowly think about that with this lesson, but that really is the crux of it. We want to basically do this projection step to find out what our new error function is, and then we're going to take derivatives of each one of these P of N's, G of N's, set them all to 0, and then come back with that updated guess and do it again, and do it again, and do it again, okay? So then it's a matter of just taking this derivative. And so if you notice that we have this S minus S prime summed over all M and all N. And then remember that the amplitude squared of something is just that thing times its complex conjugate, which we've written here. And we can expand all of that out. And so for instance, if we take the derivative of M with respect to P of N, then there's basically only one N term that has P of N in it, right? That's just this one N term, and then that leaves us with a sum over all M. So now we have this as a sum over all M. And if we take this derivative, it would be equal to this whole function we've written out here, okay? This is really not that complicated. I think if you just sat with it for a little bit, go back to calculus 1, this really just falls right out. It's important to note that you have these star terms here. That just denotes complex conjugate. That's all I'm using that for here. So now if I write this out, I'm actually including the complex conjugate here. So that's why I get these two terms, right? And what you'll note is this number here and this part here, they're actually just complex conjugates of one another, okay? So generally, if I want to solve that this derivative is equal to 0, then this sum here and this sum here, they're just complex conjugates. So in general, if one of them is 0, the other one also has to be 0, right? So, and that is all we're saying is, right, nothing more complicated than that if A equals A plus JB equals 0, then A conjugate equals A minus JB is also equal to 0, right? And why is that the case? Well, that's because this A and JB term, so they're orthogonal, right? Like this is the complex part, this is the real part. The only way that this is 0 is both A and B have to be 0. So you have something plus its complex conjugate. So that what does that mean? Basically, it means that I can drop this term. So that's why, don't be confused. We drop it because it's basically the same thing for all intents and purposes when we set it to 0. So then we have the sum of all these G's and P's here. And this is all equal to 0. But what's interesting is I have P here, G, and then this subtraction. This is actually pretty easy to rearrange, right? And I can actually solve for P of n. This is a sum over m. This P of n can come out to the outside. So what does that mean? That means I can just simply solve for P of n, and I get this nice solution here. It just drops out. And so what it's telling us is that each term in P is related to this sum of all the terms of G and S prime summed over M. Okay, that's pretty interesting. So that means that the P's are related to the G's and our spectrogram, right? And I leave it as an exercise to show it, but you can do the same thing for G, but a little bit more tricky, not too much more tricky though, to show that it's simply all the P's, right? And also our S prime, our spectrogram. So we can sum over all M of all these P terms and the amplitude squares of all the P terms, and boom, I can get each value G of K. Now there's a little subtlety here when you sum over this, and that is that, again, when you discretize these functions, we can't keep going to plus minus infinity. We have to truncate it. So our pulse and our gate are only so long, right? So what we typically do is we take this gate as being longer in terms of number of samples than the pulse. And what we can do is we can visualize that here. Let's give ourselves a new page. We're going to say that we have some pulse here, and it's broken up into indiscrete samples. This will be our P of n. And then we're going to slide it across our gate. And our gate is going to be sampled at the same resolution, right? Okay, so this is kind of just roughly showing you that this is sampled, so we'll call this G of n, right? And so notice that these two line up here, right? And that would be, this would be summed over these P's and G's here, then we would shift by 1, right? And that would be a shift by 1. I'm not lining these up perfectly. This is just a drawing for demonstration. You'd shift by 1, you'd shift by 2, you'd shift by 3. This P then shifts. You have this here and this here. This P then just keeps shifting this way, right? And it goes through all of the G values. So basically the length of G minus the length of P, right? So let's say that P has n values. Let's say that G has K values, and these are capitals. And then delay has capital M values, where capital M is equal to capital K minus capital N. Okay, so that's basically telling us that we're just going to have M delays where we can shift this P through G, right? So the reason I'm saying this is just because when you think of this shifting in this summation, you have to remember that I can never sum outside of my bounds of P, right? I only have access to this many terms at any given time. Well, that's fine because this is a short pulse and it's only defined over that period of time. Everything else is zero anyways. It puts a couple of restrictions on things. And I discussed that in kind of detail here. So UCG is length n plus m. You have m number of delay steps. It's all the same as I was just discussing. And I think the two things that come out of this is when you look at the summation over G, you can get into a little bit of trouble in that you have this K minus M term, which means that if you allow M to go too high, you want P of a negative value, and that can't happen. So we just want to prevent that. We also want to prevent that if this is just summing over zero terms here, so we can't go below zero, but what if K is less than M to begin with? So we can't have that either. So that's problematic. So we can't have a divide by zero. And so there's a couple of things that ended up popping out of that. And that is that we can fix that by just ignoring the first and last n over 2 points in G. So basically we don't even look at K until it gets above n over 2. And we don't look at it beyond the last point minus n over 2. So this G of K term, you just set it to 0. So that first n over 2 terms of G. So the first n over 2 terms of G, let's say it's here. You just assume that, and then the last n over 2 terms, let's assume it's here. So this would be n over 2. This duration here would be n over 2. You basically set these, I'll actually mark this in red just so it's clear. Yeah, you just assume that these are 0, right? That's fine. G is going to be short. It's going to be somewhere in the middle here anyways. So you assume that that's 0. That helps you here with this, preventing this divide by 0 here. And then you also make sure that M is always chosen such that K minus M is within the bounds of 0 to n. Part of that is taken care of by ignoring these first n over 2 points, but this is just a simple statement. Basically, this K minus M must be inside of P, right? Otherwise, it's 0, it doesn't matter. So we just have a check to make sure that this is true. If we ensure that both of these are true, then this works out. And I encourage you to look back through the code for the calculation of next G. So that's the function that calculates the next value of G from the current values of P and S prime. I encourage you to go back and look at that for the implementation. It's actually not too complicated, but this is just another example of whenever you discretize something, and you remember this from if you have gone over how you actually do like a discrete Fourier transform, right? Whenever you discretize something, there's always sort of nuances that have to be taken care of, and this is part of it. So then we have a final set of procedures. One is that we do this projection to get our S prime. 2 is that we calculate P. 3 is we project again, and this is how we're going to do our retrieval. It's a little bit more efficient. We project again to get our new S prime. Then we calculate our next G, and then we go back to 1, right? We project again, get our P, project, get our G, project, get our P, project, get our G. We just keep going through this process over and over. And what's going to happen is that all the terms in P and all the terms in G, they will slowly start to converge to their true values if everything is set up appropriately. So our final step is to actually put this into action, right? Now we have this solution for P and G based on this S prime, and we know how to get that S prime through this projection step, okay? So let's go through an example of actually putting this into action. So we can do that by calculating a spectrogram, and I'm not going to run through this step by step, but I show the code here for calculating some measured intensity spectrogram. Then what we're going to do is we're going to run a least squares algorithm on that. And so I do want to just show a couple of these functions that we have available. This calc SF is for calculating the frequency spectrogram of S for a current P and G. This calc ST is the time domain spectrogram. So if you notice what we're doing is we take our time domain spectrogram from P and G, convert it to F, take the amplitude squared, and that's our measured spectrogram, okay? And so the way we get our measured spectrogram is that we actually are assuming some two inputs. So these are our actual real pulse and gate functions here that we are wanting to retrieve. So we're going to assume that our code, our retrieval code, doesn't know what those are, right? But this is our ground truth, right? So this whole step here is setting up our ground truth. So we have some P, we're putting on some complicated quadratic and cubic and quartic phase, right? So it's some very complicated phase that we're putting on it here. And then we have this G function, which also has some quadratic phase here. So it's also not transform limited. So we're breaking that assumption from before and making it more general. So now we have our measured spectrogram. So this is our ground truth spectrogram, right? Or I shouldn't say that, it's really just, yeah, it's our measured spectrogram that we would have like in a real measurement, right? Because we wouldn't know P and G in a real measurement based on those two values. So the next step then is to do a retrieval on that. So what we do is we start with a guess, like I said earlier, and we just guess two transform limited 20 femtosecond pulses. Okay. They have no phase. So we have no knowledge of any phase ahead of time. We're just guessing something transform limited. And then we have to define this projection S proj, and that's just going to be our S prime matrix from above, right? So that's our projected spectrogram, okay? So the steps are basically what we already described. What we do is we project, then we calculate the next value of P based on the current value of G and that projected spectrogram. We do this step just to make sure that the intensity doesn't run out of control. There are some degenerate things to be careful about. For instance, time delay, as long as they both have the same relative delay, doesn't necessarily matter, it's not going to show up. The second thing is intensity doesn't matter because it's kind of relative. So you can imagine that if I have a pulse that's 10 times the peak intensity than what it actually is, so long as my gate is 1/10 of its actual peak intensity, then I'm fine, right? So you don't want that to run out of control. So we normalize our P to 1 to have an amplitude of 1. So their relative amplitudes is what matters, not their absolute amplitudes. So then we project again based on that new updated P value. And then we calculate our next G value based on that newly calculated P value and the new projection of S. And then we just iterate this over and over and over and over, okay? Now I have this little convenience thing here that what it's doing is it's basically just saying that every so many frames, every so many iterations to grab all the data and save it so that we can kind of make a movie and watch it. And so that's exactly what we do here. So let's run through what this is here. At the top left, we have the measured spectrogram. It looks kind of funky. It's not so straightforward to determine what's happening. Remember, both P and G are not transform limited. So all those assumptions from earlier, you can't retrieve, right, what the spectral profile is of P and G from just looking at this. But this is our measured spectrogram. This is our initial guess. Remember, our initial guess is all transform limited, so we have this flat pancake, right? So that's these two panels, so are measured and retrieved. And right now it's at our initial guess, we're at step 0, right? So then down here in the bottom left, these are our amplitude functions of G and P. So this is the current G, the current P. These solid lines are the actual P and G values here. So this actual P value is kind of hidden by these data points of the guess. I could have made the guess even different. It would have still worked. Over here, it's the same thing in terms of the color coding. The only difference is that this is the derivative of the phase. Now remember, what we retrieve really is truly the derivative of the phase, not, because it's not going to retrieve that constant offset term, phi naught. That is not going to change. You can actually play with that. If you put a constant offset phase in P and G, it will not change the spectrogram because you're taking the absolute value squared of it. So really, we only have access to the derivative of the phase in time. So to within a constant offset. And so of course we start transform limited. These are just flat lines, but these are the actual values, these solid lines. So now I'm going to play it. We do up to 300 iterations. And so you notice that almost instantaneously it pops into something very close to the measured spectrogram. And then over the next 200 or so iterations, it slowly improves this phase value and the amplitude values until we converge to the actual pulsing gate. So you see over time, slowly, we just keep improving, keep improving, keep improving the fit between these two, right? That's actually what we're fitting. Don't forget that is the squared error between these two. By doing that, we come to a pulse and gate, calculated pulse and gate that almost perfectly match our inputs. And this is pretty, you can play with this. You can move everything around as long as you don't break some sort of assumptions or things, taking care of in the discretization. This is pretty robust. It will always work. So I can grab this slider. I would encourage you to do this. You can just kind of walk slowly. So if you pop one step over, that's going to 6, we're doing 6 iterations per step. Within 6 iterations, it already has this general shape. There's just a lot of details here that are missing. If we go forward to about 50 iterations, you see it started to almost like a zipper, improve the phase here and here. And we're starting to slide in around these true amplitude values. But we notice the spectrogram already looks much closer to the reality by fitting the phase. So the phase is actually more important to a lot of the details within the spectrogram than the amplitudes. Now we move forward, you notice that now we're starting to converge closer and closer to the real amplitudes. Note that the phases only really matter where the amplitudes are high. So when you have these really low amplitude values, the phases don't matter too much. They're the last ones to fit. So really those take a lot of iterations, but if we keep going, keep going, keep going, everything moves into the wings, and then you have a nice fit all the way across. Over here, you see a little bit of divergence, but note, there's almost no amplitude over there. So it really, the phase almost has no meaning. So the last thing that we can look at is we actually tracked the error as a function of iteration. So this is something kind of interesting, and this is generally true of these techniques, is that it kind of goes in fits and starts. You've got a very fast fit, right, within those first few iterations. It plateaus a little bit, then it fits rapidly again, plateaus a little bit more, and it has this final fit up to the 300th iteration. This brings up a good point, though. Notice we could keep going, and it would keep getting better. So what are the limitations to this? Well, in reality, you would have some noise, right? So this M would start to plateau as you hit the noise floor, right? So if we're pushing for improvements that are improving within the noise, so if I imagine adding noise to the spectrogram, and I can encourage you to take this code and maybe try this, add some noise to the spectrogram, then it's going to keep trying to improve to reduce that squared error. But at some point, that squared error is going to be almost purely due to the noise. And at that point, it's going to be meaningless what changes I'm making to PNG. In fact, it will actually start introducing noise to PNG to try to fit. So that is actually a cause of noise. The noise in the spectrogram leads to noise in PNG. You could put physical constraints such as energy frequency filtering to make sure that that noise is physical. If it's outside of the bands of the spectrum or something like that, and that might help a little bit. But anyways, that would limit the fit, this error. So this would start to plateau. But it's a generally true statement that these phase retrievals, this is techniques, this is one issue, is that when do you stop, right? Usually I like a relative error thing where you say that I want the change in the error relative to the error value right now, so like a % difference change per iteration to be below some threshold, but that threshold is arbitrary. So you pick a quality of the fit that you want, and it will give you a fit to that quality. Whether that quality is good enough to accurately represent the amplitude and phase is another thing entirely. And I think that that is usually determined just by running simulations like this. Also, it's really important to put in some physical constraints. So just because I get a pulse negate out, right, does it really match other physical measurements? Can I look at a spectrum of my pulse and a spectrum of my gate and make sure that it actually matches those separately obtained spectra. That's another way that you can enforce some quality on your fits. So it is one downfall of these generalized phase retrieval algorithms. All right, so that brings us to the end of this lesson. I'd like to thank you for listening and hope you have a great day.